When you think about saving a file, there's usually this lingering expectation of physical reality, you know?
Yeah, definitely.
Like you hit save on your laptop, maybe you hear the fan spin up a bit, and you can practically point to the exact piece of silicon where that document lives. It's almost like putting a manila folder into a metal filing cabinet.
Well, it feels tangible because, I mean, for a really long time, computing was tangible. The data was actually sitting on a specific disk in a very specific server rack.
Right, but the moment you step into the world of massive global applications, the high-frequency trading platforms or, global streaming services, that physical filing cabinet just completely dissolves.
Oh, absolutely. It's a distributed maze.
Yeah, we're looking at an architectural landscape that is entirely invisible, constantly shifting, and somehow handling millions of transactions a second without ever dropping a single piece of data.
The data isn't sitting in one static location at all. It's dynamically moving across an entire grid of machines.
And to figure out how this invisible machinery actually works, we are diving into the architectural blueprints of Apache Ignite today.
Right. Specifically, we're looking at Chapter 4 from the Apache Ignite book by Shamim Bouillon and Michael Zalutkov.
Exactly. And our mission for this deep dive is to basically demystify how these modern, massively scalable distributed databases actually work under the hood. It's sort of a shortcut to understanding enterprise-grade architecture.
And we're going to focus heavily on the mechanics here, not just, what these systems do, but the actual how and why behind the scenes that keeps them from just collapsing under their own weight.
So whether you're prepping to scale an application or trying to understand big data buzzwords, or you're just wildly curious about how big tech keeps systems running fast without crashing, this deep dive will give you that underlying foundational context.
And I think the best place to start is at the macro level, right?
Yeah, let's zoom out.
Before we even look at how data is stored, we have to look at the physical computers themselves and how they talk to each other. Because the defining characteristic of Ignite's architecture is that it's a shared nothing grid.
Which is a massive departure from older systems. I mean, legacy database models usually had this strict master-slave dynamic.
Right, exactly.
You'd have one heavy-duty coordinator node directing all the traffic, just telling all the secondary nodes exactly what to do.
And that master node was essentially a single point of failure. If you think about like a high-pressure restaurant kitchen.
Oh, I love this analogy.
The legacy model is a kitchen heavily dependent on one dictatorial head chef. Every single ticket goes through them. Every plate is inspected by them.
Okay, let's unpack this. The bottleneck becomes obvious immediately, right? Because if that head chef calls in sick or just gets overwhelmed by a sudden dinner rush,
The entire kitchen grinds to a halt.
right. The line cooks might be perfectly fine, but they have no one telling them what to do.
Exactly. So in a shared nothing architecture, you just eliminate the head chef entirely.
Just get rid of them.
Boof, gone. Every server node in the cluster is identical. They're all peers. They communicate dynamically with each other to balance the load, process queries, and store data.
So the line cooks are just perfectly communicating peer-to-peer to get the orders out. If one line cook drops their station, another one just steps in and takes over the tickets.
That's the idea. Resiliency and high availability are the primary goals here. You can unplug a server from the rack or add 3 new servers to handle a spike in traffic, and the cluster just automatically rebalances itself.
Without any central authority having to dictate the terms. That's wild. But
Right.
even without a master node, these peers do have different roles depending on how you configure them, right?
Yeah, they do. The blueprints outline 2 main types: server nodes, which are often called data nodes, and client nodes.
Gotcha. So what's the difference in practice?
Well, server nodes are the heavy lifters of the cluster. They store the actual data partitions, they run the compute tasks, handle caching. They're the structural foundation.
And the client nodes?
Client nodes are typically embedded right into your application code. They don't store the primary data. They act as the gateway. When your app needs something, the client node just routes that request to the correct server node.
Which brings up a really crucial architectural decision the source talks about. Where do these nodes actually live? Because they contrast an embedded deployment with a standalone, real cluster deployment.
And the implications for stability there are huge. In an embedded deployment, your Ignite node shares the same JVM, the Java virtual machine, as your main application.
So it's living inside the exact same process space.
Exactly.
Which, I mean, seems convenient if you just want to get something up and running quickly on a single machine.
Convenient, sure. but incredibly dangerous for enterprise production. If your application crashes, say it hits a fatal memory leak and takes down the JVM, your
Uh-huh.
database node dies right along with it.
So the application takes the data layer down in a murder-suicide. Not great for high availability.
Not at all.
Hmm.
Which is why the standard is a standalone cluster. Your server nodes run in their own dedicated JVMs, completely isolated from your app logic.
Like using Kubernetes or VMware to host them separately?
Exactly. So if your application crashes because of a bad code deployment, the database grid doesn't even blink. It just waits for the app to reboot and reconnect.
All right, so we have this incredibly resilient, bossless grid of independent nodes, but that introduces a massive logistical nightmare, doesn't it?
What do you mean?
Well, if I'm a client node and I need to retrieve a specific user profile, say user ID 8675, how do I know which of the 100 server nodes actually holds that data? There's no head chef I can ask.
You don't ask anyone. You calculate it yourself.
Wait, really? Every time?
Every time. This relies on what's called a distributed hash table, or DHT. Every node in the cluster knows the overarching topology, like they know how many nodes exist in total.
Okay.
So in a traditional basic DHT, you take your key, which is user ID 8675, you run it through a hashing algorithm to get a really large number, and then you do a simple modulo operation.
The classic division remainder math. You take the hashed key, divide it by the total number of nodes, and whatever the remainder is, that's the bucket or the node that holds the data.
Exactly. It's fast, elegant, and requires zero network traffic to figure out where data lives. Any client node can do the math locally and immediately know exactly which server to contact.
Okay, hold on though. If the math relies on the total number of nodes as the denominator,
Yep, you're seeing the problem.
what happens when a node crashes? If we had 100 nodes and one goes offline, the denominator is suddenly 99. The entire mathematical equation changes.
It completely breaks the system.
Because if I run that exact same user ID through the formula and divide by 99 instead of 100, the remainder changes. My data isn't on node 42 anymore. The formula says it should be on node 15.
And this is the fatal flaw of a basic distributed hash table. It triggers what we call a rehashing storm. If a single node drops out, or even if you add a new node to scale up, the location of virtually every single piece of data in the entire database gets recalculated to a new bucket.
Oh, wow. So the cluster would spend all its time just shuffling terabytes of data around across the network just to satisfy the new math.
Exactly. The network would completely saturate.
Yep.
The database would be functionally offline.
So how do you actually fix that? Because obviously these systems do scale.
To solve this, enterprise distributed databases abandon that basic modular math and use a solution called rendezvous hashing.
Sometimes called highest random weight hashing, right?
Right.
I was actually looking at the mechanics of this, and I gotta say, it seems incredibly CPU intensive. Wait, so instead of just doing a simple division problem, rendezvous hashing takes the data key, combines it with the ID of a specific node, and hashes them together to generate a random weight or score.
That's right. And it does that for every single node.
Wait, so basically running a mini lottery for every single piece of data. If I have 100 nodes, I'm running 100 separate cryptographic hashes just to figure out where one single user ID goes.
Yes, and whichever node and key combination generates the highest random score wins the data.
But doesn't constantly running math lotteries for millions of keys slow the whole system down? I mean, isn't that going to absolutely choke the CPU?
It's a brilliant observation, honestly, because it highlights a classic computer science compromise, the time-space trade-off. Yes, calculating 100 hashes per key requires significantly more compute power than a single division operation.
So why willingly take that performance hit?
Because CPU cycles are cheap and network bandwidth is expensive. Let's look at your crash scenario again under rendezvous hashing. Say node 2 goes offline.
Okay.
The client node needs to find user 8675. It runs the hashing lottery again, but this time node 42 just isn't in the drawing.
So whoever had the second highest score originally is now the winner.
Exactly. And here's the magic part. What happens to all the data that wasn't on node 42?
Oh, I see it. If a piece of data was sitting on node 15 and node 15 originally had the highest score, node 42 disappearing doesn't change that. Node 15 still has the highest score.
Bingo. Only the absolute minimum amount of data, the stuff physically residing on the failed node, needs to move. It gets assigned to new winners. The other 99% of your data stays exactly where it is.
So no network storm. No terabytes of shuffling.
Exactly. You trade a microscopic fraction of processing speed to guarantee that your system can dynamically scale up and down without tearing itself apart.
That is such an elegant solution to a catastrophic problem. You're just shifting the burden from the physical network cables to the
It's
processors.
the only way to do it at scale.
Okay, so rendezvous hashing has run its lottery, and it tells our client node that user 8675 belongs on server node 15. Let's zoom into that specific machine. How is it physically organizing this data in RAM so it doesn't run out of space?
So Ignite relies on a highly structured, durable off-heap memory architecture. It prevents the Java garbage collector from constantly freezing the system.
Basically manually managing memory in a hierarchy, right? Kind of like game of Tetris.
Very much like Tetris. And the fundamental building block, the smallest atomic unit, is the page.
And these are fixed sizes, right? Like 4 kilobytes.
Yep, standard 4KB pages. Now you have data pages, which hold your actual key value entries. But you immediately run into an interesting mechanical problem. What if user 8675's profile is packed with history and it totals 10 kilobytes?
It can't fit in a 4KB page. Does it just get rejected?
No, it fragments. The system intelligently splits that single key value pair across multiple pages, chaining them together.
Oh, got it.
It introduces a slight read overhead, but it ensures you aren't wasting massive blocks of memory on tiny entries just to accommodate the occasional large entry.
But if you have millions of these 4KB pages scattered around RAM, how do you find anything quickly? I mean, you can't just scan them one by one.
You use index pages, and this is where we get into B+ trees.
Right, B plus trees. I feel like people hear that term and just assume it's generic indexing, but the underlying structure is what guarantees the low latency.
Absolutely. A B+ tree is basically a massive self-balancing table of contents. Instead of a flat list, it's hierarchical. You have a root page that points to internal branch pages, and those branch pages point out to the millions of leaf pages where the actual data lives.
So instead of scanning a million pages, the system checks the root, which says, oh, user ID 8000 to 9000, go to branch page 3.
And branch page 3 says, user 8600 to 8700, go to leaf page 40. Blindingly fast.
Okay, so we have pages, which are organized by B plus trees. But the operating system doesn't dole out RAM 4 kilobytes at a time, does it?
No, that would cause massive fragmentation at the hardware level. When Ignite needs more memory, it asks the OS for a segment.
A segment being a contiguous block of physical memory.
Right. Typically starting around 256 megabytes, the system then internally chops that 256 megabyte block into thousands of 4KB pages.
And managing which of those pages are full versus empty requires its own tracking system. The source details something called free lists.
Yeah, a free list is essentially a live inventory. If data gets deleted, its page becomes free. But instead of just keeping one giant list of empty pages, Ignite maintains multiple lists categorized by how empty they are.
Oh, really? Like a list for pages that are 25% empty, another for 50% empty?
Precisely. If new data comes in that needs exactly 1 kilobyte of space, the system doesn't waste a completely empty page. It looks at the free list, finds a page that is 75% full, meaning it has exactly 1 KB left, and slots it in perfectly.
Wow. Maximizing memory utilization down to the byte. So if I'm picturing this whole hierarchy, a region is the top level, right? It's like a giant bookshelf.
I love that analogy, yes.
The segments are the individual shelves on that bookshelf. The pages are the actual books on the shelf. And the free lift is just a live inventory telling us which books still have blank pages left.
That is exactly right. And the obvious question is, why bother with multiple bookshelves? Why not just pool all your segments into one massive region and let the system figure it out?
Right. Why overcomplicate it?
Because of the realities of data lifecycle. Not all data provides equal value. Imagine you're running a massive e-commerce platform. You have your products table. That is hot operational data.
Right. Users are querying product pricing and availability millions of times a second. That needs to be served from RAM instantly.
But you also have your purchase history table. It's a massive data set, logging every transaction from the last 5 years. It's important, sure, but an individual user might only look at it once a month. It's cold historical data.
Oh, I see where this is going. If you put both of those on the exact same bookshelf.
As users gradually click on their purchase histories over time, the system is going to pull those cold records into memory. And eventually, that massive volume of cold data will poison the cache.
It'll eat up all the RAM, pushing out the hot operational data.
Exactly. Suddenly, your main storefront is running sluggishly because it's having to fetch product prices from the hard disk.
So by configuring regions, you build physical firewalls in your memory. You can set hard limits, so high-priority data always has room to breathe.
Right. You can say, I am dedicating a 128 gigabyte region strictly for products, and a separate 4 gigabyte region for purchase history. If the purchase history region fills up, It only evicts older purchase histories. Your product data remains completely insulated.
Okay, so we have this perfectly orchestrated RAM architecture. Things are organized beautifully on our bookshelf. But the elephant in the room with in-memory computing is volatility,
Right, RAM requires continuous electrical current to maintain state.
which introduces the nightmare scenario. You are in the middle of a complex financial transaction. You need to deduct $1,000 from account A and add $1,000 to account B.
A classic atomic transaction. They must both succeed or neither can happen.
So the system successfully deducts the money from account A, updates the page in RAM, and before it can update account B, someone trips over the server's power cord. The machine goes black.
And when that server eventually reboots, if you don't have a recovery mechanism, your database is corrupted. The books don't balance.
Right. Account A lost money, and account B never received it. It's just gone.
The source outlines 2 historical approaches to surviving this amnesia. The legacy method is the undo log.
Which is basically saving the old value to roll back if a crash happens, right?
Yeah, before you touch account A, the database physically writes down account A's old balance onto the hard disk. Then it updates RAM. If the system crashes mid-transaction, upon reboot, it checks the log, sees a half-finished operation, and uses that saved old value to overwrite the mistake.
It rolls the state backward.
Exactly. But Ignite and most modern high-performance databases use the exact opposite approach, the write-ahead log, or WAL.
Okay, so how does WAL handle it?
Write-ahead logging dictates that before you ever touch the data pages in RAM, you take the new intended values, deduct $1,000 from A, add $1,000 to B, and you append them to a sequential log file on the physical disk.
So you write the intended values first?
Yes. You commit the log, ensure it's permanent, and only then do you let the system update the actual database in RAM.
Oh, I get it. So an undo log is like keeping your receipt so you can return a bad purchase. But the write-ahead log is like writing your grocery list in permanent ink before you buy anything. If you suddenly get amnesia in the store, you don't return what's in your cart, you just look at the list and finish shopping.
That is exactly right. On reboot, the system reads the WAL, replays the exact sequence of events, and reconstructs the data pages exactly as they should have been. It rolls forward.
But wait, if you're trying to build a blindingly fast in-memory database, why introduce the hard disk into every single transaction? Doesn't waiting for the disk to write the log defeat the purpose of using RAM?
It's a great question, and it comes down to the physical mechanics of hard drives and SSDs. If you were constantly updating the actual data files on disk, you'd be doing random I/O.
Right, jumping around the disk doing random in-place updates.
Exactly. The drive controller would have to hunt for account A's location, write, then jump to account B's location and write. Random writes are notoriously slow.
Because it requires seeking.
But a write-ahead log is strictly append only. You are just writing to the very end of a single continuous file. The disk never has to seek.
It just streams data linearly.
Right. And sequential disk I/O is orders of magnitude faster than random I/O. It gives you bulletproof durability without sacrificing speed.
Wow. So the WAL gives you the absolute durability of a hard drive with a minimal latency penalty, preserving the performance of the RAM layer.
It's the essential compromise that makes distributed in-memory architectures viable for enterprise.
Well, this has been a massive journey into the weeds of system architecture. We started with bossless, shared nothing grids, right?
We did.
Then we explored the mathematical lotteries of rendezvous hashing to distribute data without network storms, organized our RAM into pages and regions to protect hot data, and finally, we amnesia-proofed the whole thing with write-ahead logs.
It is a phenomenal stack of engineering solutions. And if you're listening to this, the practical takeaway is really just understanding the sheer volume of invisible work happening under the hood.
Right, it's not magic.
Exactly. When you swipe a credit card or load a wildly popular app and it works instantly without failing, it's not magic. It's this exact invisible architecture working flawlessly behind the scenes.
It completely reframes how you view software. And, there's one final philosophical consequence to all of this that I just keep coming back to.
Oh, yeah. What's that?
Well, the source material notes that if a node dies, data automatically redistributes across the cluster based on backup copies.
Right. The grid heals itself.
Exactly. Which raises an incredible question. If a database can constantly self-heal, seamlessly shifting its data across random hardware around the world based on mathematical weights, at what point does a database cease to be a physical place and instead become just a continuous floating mathematical agreement? It really makes you realize that the filing cabinet isn't just gone. It never really existed at all. Something to think about the next time you hit save.